All right, welcome to our next lesson. We're going to talk about the biogeochemical cycles today, which sounds super complicated, but it is the carbon cycle, nitrogen cycle, phosphorus cycle, and the water cycle. So learning goal is that you will be able to describe the biogeochemical cycles, including all of the ones that I just listed. So let's talk about what biogeochemical cycles are first. So they are natural processes that involve the cycling of essential elements through the atmosphere, lithosphere, hydrosphere, and biosphere. So through the earth where everything's living and then up through the atmosphere. These cycles are vital for maintaining Earth's ecological balance and for sustaining life. We're going to talk about the carbon cycle first. This is a really big one, especially in this class. We're going to talk about the human impact on things. But the carbon cycle is the biogeochemical process that describes how carbon moves through various reservoirs on Earth. So carbon sources and sinks. The sources are going to be that carbon's released through natural processes and human activities. So cellular respiration, we're releasing oxygen or carbon. And then when we are burning things, including fossil fuels, we're releasing a lot of carbon as well. And then sinks, so where is it stored? So natural systems that absorb and store carbon are going to be forests and oceans. So the key processes, we have photosynthesis, so plants and algae convert carbon dioxide into inorganic compounds using sunlight. So we're going from a gaseous carbon into a more solid carbon in those sugars. Respiration, organisms like us release CO2 during the process of respiration. We take in oxygen and release carbon as we're breaking down the sugars in our bodies. Combustion is going to be burning, so burning fossil fuels and biomass. Biomass is any mass that was living, like wood, grass, things like that. That also releases carbon into the atmosphere. And then we have decomposition. So anytime something dies or decays, it's the breakdown of organic matter, and that returns carbon to the soil to begin again. So first, plants use carbon dioxide, which is inorganic carbon, during photosynthesis to produce sugars. Oxygen is produced as a byproduct. Herbivores then eat plants, break down that complex organic molecules into simpler building blocks and incorporate those molecules into their structure. They grow and build using the food that they ate. And respiration produces CO2 and water and releases those compounds back into the atmosphere. The decay process of decomposers involves respiration and therefore recycles organic molecules. And then carbon sinks are processes or situations that remove carbon atoms from active short-term nutrient cycles and store them for extended time periods. Examples are carbon stored as fossil fuels, sedimentary rock, or bodies of long-lived plants. So this is where carbon should stay for a very, 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 very long time. And this is one example of a carbon cycle. So if we start with carbon dioxide, it is being taken down through photosynthesis, which is then either ingested by herbivores or is broken down by detritivores. Then that deer can also get eaten by mountain lion, whatever it is. And then they respirate, which releases carbon dioxide back into the atmosphere. This would be the natural carbon cycle without any human impact on it. This is natural process what the carbon cycle should look like. But we have impacted the carbon cycle. So burning fossil fuels takes carbon atoms that were removed from the carbon cycle. Fossil fuels are carbon sinks. That's where carbon is stored for very, very long periods of time under the surface. And because we're burning them, we are reintroducing them into the active cycle. So what was supposed to be kind of saved away and not out in the air in the atmosphere, we have burned and released. Another way is that we were converting forests, another carbon sink, less long-term but still long-term, to agricultural land. Trees hold a lot more carbon than any of the crops that we're growing. Agricultural land where you harvest that, so that's really short-term storage. And that has increased the amount of carbon dioxide in the atmosphere because there's less plants, big trees, long-lived trees to store that for long periods of time. And the consequences are that we have rising CO2 levels, so rising carbon dioxide in the atmosphere, which leads to global warming and climate-related issues. And this is the carbon cycle with us involved. So here's that, what was there before. Here's our long-term storage, our sinks underground. We are harvesting that to burn, so combustion, releasing more CO2 into the atmosphere. I mentioned earlier that the ocean is a carbon sink. We'll talk about that a little bit more in a later chapter, but ocean absorbs some of that CO2 and cycle continues. But the biggest thing is that this carbon should not theoretically be in the atmosphere, but because we're using it to produce energy, it's making its way over there. All right, so for the nitrogen cycle, there's a lot of definitions for this one. But nitrogen cycle involves the cycling of nitrogen atoms between abiotic and biotic ecosystem components. Producers are unable to use atmospheric nitrogen, which is N2. They have to get nitrate or ammonia. So we have nitrogen-fixing bacteria that help make that happen. So nitrogen-fixing bacteria convert nitrogen gas into ammonia, and decomposers also break down nitrogen-containing molecules, also releasing ammonia, making it available for plants. Nitrogen fixation is the conversion of N2 into ammonia by bacteria. Nitrification is the conversion of ammonia into nitrate and nitrite by soil bacteria. Hopefully you're remembering your chemistry right now. Denitrification is converting nitrates back into atmospheric nitrogen. And ammonification is breaking organic nitrogen compounds into ammonia. So there are the process of doing that thing and then the things that actually do it. So the different kinds of bacteria and then the processes that they are doing. So nitrifying bacteria are able to convert ammonia into nitrate, which can be converted into nitrate. And then denitrifying bacteria are able to, under anaerobic conditions, so no oxygen, convert nitrate into nitrogen gas, which is then released back into the atmosphere. The primary sink for nitrogen, most of the nitrogen that exists on Earth is actually in the atmosphere. 70% of the air that we breathe is nitrogen. And this is that nitrogen cycle. So we have nitrification, bringing it down to the soil, and then switching over to ammonia. So that's used by plants, which is then eaten, and then is broken back down, and then might go back to the plants, or it could go to denitrifying bacteria back into the atmosphere. So human impact. We use nitrogen because plants need nitrogen to grow. We use nitrogen in our fertilizers a lot. So if too much nitrogen is applied as fertilizer, or if it is applied at the wrong time, a lot of that fertilizer is actually going to be carried into aquatic ecosystems. The presence of these nutrients increases the growth rate of bacteria, algae, and aquatic plants. And toxic algae can kill fish and poison humans. So we want plants in these lakes and rivers and aquatic places, but some of them can be toxic, and if there's too many plants, then it kind of outcompetes the fish. Increase in the number of plants and algae results in lowered oxygen concentration, which creates dead zones. So even though plants and algae release oxygen, they also are dying and decomposing, which takes up that oxygen. And growing crops that have nitrogen-fixing bacterial as symbionts can increase nitrogen in the soil, which we will talk about again in a later chapter. Animal manure can also be used as fertilizer, or it can become a pollutant. So when we have those oxygenation that ends up in lakes and rivers, that's what we get eutrophication, which is nutrient runoff that causes excessive plant growth in bodies of water. And there's also air pollutants. So NOx, that just means it could be nitrates or nitrites, contribute to smog and acid rain. All right, I'm going to pause here. We have 2 more cycles to talk about, but we're going to make that a part 2. So let me know if you have any questions, and I'll see you in the next one.